stuff. How you doing? Right, quick straw poll. How many of you are here because you know what a ray tracer is? How many are here because you love JavaScript? How many are here just because you saw the word shiny and thought, I'm going to go to the shiny talk. That looks shiny. Welcome. My name is Dylan Beattie. I run a company called Versatile. I do training and consultancy and microservices, all kinds of stuff. I'm a Microsoft MVP. I run the London.NET user group, and I once invented a programming language in a bar as a joke so that everyone in the world can be a rockstar programmer. And if any of you want to get your rockstar certification stickers, come and see me afterwards. I have some of those here. Now, I've been introducing people on this stage the last couple of days, right? And I was like, well, I don't really want to introduce myself, so I thought I'd ask the internet, specifically the comments on YouTube, about me, so I can introduce myself and all of you can sort of get an idea of who I am. So I cherry-picked some YouTube comments. This is a dude is a tosspot, annoying voice and overinflated ego. So now Data Fabric's there. He doesn't look like a well man, right? This one, I had no idea what this meant, so I had to ask some children. Apparently, I am the absolute mad lad Sigma Chad in the coding realm. Apparently that's good. I don't know. I don't even know what a Chad is, let alone a Sigma Chad. And probably my favorite thing anyone ever said about one of my talks on the internet, shit, Tyrion and Jon Snow had a baby. And yes, today we are going to talk about ray tracing. Now, ray tracing is a computer graphics technique for creating photorealistic images. And it is well known for two reasons. One, it looks fantastic. If any of you have seen Pixar, the animation company that actually, not a lot of people know this, Pixar is what made Steve Jobs a billionaire. Apple kind of came later. It was Steve Jobs' investment in Pixar making things like this, Luxo Jr., the first mainstream computer-animated movie. If you've seen Toy Story, now, if you watch the Pixar movies closely, you'll notice every movie they have something they didn't have before. Toy Story, they're all toys because toys are shiny plastic. That was easy to render on the computers they had at the time. When they did Monsters, Inc., they'd worked out how to do fur. Now they've worked out how to do skin, water, all these different kinds of effects. The same technology was used to recreate living actors. We had digital Peter Cushing. Today, ray-traced graphics are so good that they use them to do costumes. Tony Stark's Iron Man costume, a lot of the scenes in the Avengers movies, he's not wearing it. He's wearing this motion capture suit, and then they feed it into their rendering farms, and it spits out the shiny, photorealistic, reflective Iron Man costume with all the explosions and the highlights and everything in the right place. So one, ray tracing is famous because it looks awesome. Two, it is slow. Ray tracing is incredibly slow. We're used to playing games where you want to get, movies 24 frames per second. You're playing Far Cry or Unreal, 60 frames per second, kind of cool. It means you have to generate every image in 1/60th of a second. It's common for one frame of a modern computer-generated special effect in a movie to take more than an hour to render. So 24 frames per second means each second of an Avengers movie took a day just to draw that one frame. Ray tracing is slow. Why is it slow? Because it doesn't take any shortcuts. It simulates the way light behaves in reality. Now, the way that it works, you can see me now, because there is a light source up there. It's shining light off me. The light is bouncing off me, and some of it is hitting your eyes. Now, if we were to go outside, the daylight in Lithuania here is a little bit flat and gray, but if we were to go somewhere like the Sahara Desert, there's a light source in the sky, that's the sun, and that beams out rays of light, and we go, oh, well, that one went into outer space. It didn't even come anywhere near Earth. Not a lot of use to us. Let's try another one, and another one, and another one, and another one, and we're simulating a whole lot of rays of light here that have nothing to do, and eventually, one of those bounces off an object here on Earth, but then it bounces off into outer space. But eventually, one of them bounces into our viewer here. And that's interesting because it means that person can see something. And then we take another one, and that one bounces off into outer space as well. So one of the first principles of ray tracing is we are going to optimize this. We are not going to look at any rays of light we are not interested in. We are only going to look at the ones which hit the viewer. And the way we do that is we're going to flip the whole thing around, and we're going to run it backwards. So the way ray tracing fundamentally works is we create a viewport. This is the image we are going to render. And we are going to trace a ray from the camera, from the viewer, through every single pixel in that grid and decide what color to paint it. And we're going to repeat that for every single pixel in the grid. This is one of the reasons why it's slow, is we need to do this whole raft of calculations for every single pixel. Now, some of these here, as you can see, they actually hit something. This one here, that one goes behind the red ball. That one passes behind the red ball. This one hits the red ball and bounces. We color that one a dark red. This one, this one, this one, and so on and so on. And for every single pixel in that grid, we need to use these calculations to figure out what color that pixel gets painted to build up this photorealistic image. Now, we are going to start off with this. We are going to render a camera pointing out into infinite outer space in a universe with no shapes. No, by the way, I'm going to use the word shapes because this is JavaScript, and in JavaScript, the word object already means something different. So everything in our universe is going to be a shape or a light. We're going to have lights, we're going to have shapes, and we're going to start off with 0 lights, 0 shapes. Now, we need to build a little bit of scaffolding before we can get into the guts of this thing. First of all, we are going to write a JavaScript file that models colors. We are going to use the red, green, blue color model, which is prevalent in computer science, mainly because we have RGB displays, so that's easy to work with. Now, the code for setting this up looks like this. We have a JavaScript class. It is exported. We are in ECMAScript 6 land here. This is modern JavaScript. We have modules. We can export things. We can import things. We have, anyone tell me what the hash means in modern JavaScript? It's private. Nothing else can get in and mess with our colors. They are immutable. So we have red, green, and blue, private, and we have a constructor. We say this red, this green, this blue, that makes a color for us. We have getters, but not setters. We can get those values out. We can't put them back in. We have 2 helper methods. This one here is going to return an array, red, green, blue, and something called alpha. Alpha is web transparency. 0 means you are completely see-through. You don't show up at all, which is kind of a dumb default, but the model they borrowed it from starts with that. So our default is OXFF in hexadecimal. That's 255, which is the highest allowable number in our color numbering system we got here. And we have another helper method, HTML. We have a color that gives us a string we can drop into a web page to make something that color. Now, painters will mix their own colors every time they need one. We are not at that level. This is the sort of kindergarten level of computer graphics. We want crayons. So in our color class, we are going to define a whole bunch of colors we can just use. Color.white, black, gray, red, green, blue, yellow, magenta. So we can just go, hey, give me a ball, make it color.red. And there we go. Now, light works on an additive color model. We can combine colors on a screen by adding them together. If we add red plus blue, we get magenta. We add red and green, we get yellow. Add red and or blue and green, we get cyan. We add them all together, we get white. This is what happens when you shine multiple colored lights onto a white surface, as the colors of the lights get added together. Adding black to something does nothing. Adding white to anything gives you white. Now, take a look at this image here, and what we're going to do is we are going to shine a white flashlight, a white torch, across that image, and watch the way the colors, you can see it, right? It looks normal. Now we're going to do the same thing, but we're going to use a yellow light. Now you see the way if you shine a yellow light onto blue paint, you get black. Blue light, or blue paint, does not reflect any part of yellow light. There's nothing bounces back, there's nothing to see. We get darkness. This is called the multiplicative color model. We can multiply colors together. Let's have a look at another example, exactly the same scene. This time the light is cyan. It's kind of a blue-green turquoisey color. This time, the green looks normal, the blue looks normal. The white background, well, that looks cyan now because there's this blue light shining on it. And the red paint, that's gone black because red times cyan equals black. Black is effectively color 0. And those two things multiplied together, they end up as 0. So the code that lets us do this looks like this. We've got an add method on a color. Now, colors are immutable, so all these methods give us back a new color. And this one just says, well, red plus red, green plus green, blue plus blue. Yes, it will overflow. No, the web doesn't care. If you give the web a color that's too bright, it just chops it down a size and renders it anyway. That saves us a bit of checking and error correction here. Multiplying, yeah. Red times red, and that one we have to divide, otherwise we get nonsensical values out of it. And we have a scale factor in here as well. If we want to make a color twice as bright, we scale it by 2. Half as bright, we scale it by 0.5. That's colors. We have colors. We need a way of organizing things in space. We need a way of saying where things are, and we need a way of saying where they are pointing. We are going to use something called a vector. Now, a vector, if we have a sheet of graph paper, and we want to indicate a point on that paper here, we say, well, that point is, it's 3 squares across, and it's this many squares up, And so that means that this is 3 by 4. This is the vector we refer to as 3, 4. Now, we're going to need to know how long it is. And to know how long it is, we need to ask this guy, who's so old that he's from the days when photographs were still made of marble. Anyone know who it is? Pythagoras, who invented a theorem that says you take this squared plus that squared and take the square root of that, and that tells you how long the long edge of a triangle is. Now, we need to extend this into 3 dimensions. So we are going to have x is going across the page. Y is going up the page. There we go. And Z is pointing out of the page. Z is coming towards us. If we were all wearing our 3D HoloLenses, we could actually do this in 3D. As it is, we have to fake it with perspective. But we have 3-dimensional vectors. They go this way, and then they go up, and then they go out. The coordinate system we're using here, Z means it's pointing away from you. Negative Z means it's pointing towards you, so that's actually -5. And the length of that vector, 3, 4, 5, is the square root of 3 squared plus 4 squared plus -5 squared, Pythagoras again. This, in code, looks a lot like the color. We have the x, the y with z. We also have this thing. X, y, z here is an array. That's because a lot of the operations we can do are faster if we map them onto an array and then reduce the results of that. Here's our constructor. I'm using array assignment here. Anyone want to guess why? Because it fits on a PowerPoint slide is the correct answer. There are a bunch of different ways of doing this. In JavaScript, you can do this. You can assign blocks of stuff. And it meant that this code sample would fit on a single slide, so I decided to go with it. We've got getters on those 3 properties. Now, we also need to be able to, we've defined some static vectors. These are like the Crayola crayons of 3D space. X is what's called the unit vector that points that way. Y is the unit vector pointing 1 unit towards the sky. Z is the unit vector pointing 1 unit away from the viewer. O is the origin, 0, 0, 0, the center of the galaxy, the center of the universe. Vectors have a length. We initialize that to null because we don't want to calculate it until we need it. But when we do need it, when somebody asks for it, we are going to use this thing. Question mark equals. This is the null coalescing assignment operator. It says, hey, if you got something, give it back. But if you don't got something, evaluate the other half of the expression, assign that to the variable on the first half of the expression, and return the result of it. And you're probably looking at that and going, well, what is squid? Now, squid is the squared Euclidean distance. I asked on Twitter, what do you call x squared plus y squared plus z squared before you square root it? And all the maths Twitter people went, that's the squared Euclidean distance. And I was like, I'm not typing that 100 times in a row. So I called it squid. So the squid of a vector is x squared plus y squared plus z squared. And if we want to know the length, how long that vector is, we take the square root of that thing. Now, we can do various things with vectors. We can scale them. Scaling a vector makes it longer. So this vector scaled by 2 is that vector. We can divide them. Scaled by 2 means divided by 2, make it half as long. There is a thing called a unit vector. Sometimes mathematicians call this the normalized vector, but we're going to have a thing in a minute called a normal vector, which is something completely different. So we're not talking about normalized vectors. We are going to call them unit vectors. So if we say unit, it means give us a vector that points in exactly the same direction and is exactly 1 unit in length. This is going to be important in all kinds of ways. We can take a vector, and we can add it to another vector. This gives you the result of, well, if we were to go over here and then go over here, what would be the shortcut that took us straight to the destination? This is vector addition. We have a thing called vector inversion. We can take a vector and we can spin it around, and that gives us a vector pointing in exactly the opposite direction, the same length. And we have vector subtraction, which is take this and subtract that. And subtraction actually means you take the original vector, you take the other one, you invert that, and then you add them together. It's like adding negative numbers in regular math. In vector maths, you take a vector, you invert it, you add that. That's the equivalent of subtracting. Those are the fundamental operations we are going to need. Translate them into JavaScript. We have scale, yep, x times s, y times s, z times s. Divide, the same, only it's divided by, divided by, divided by. Unit is just a vector divided by its own length. So if the vector's 5, we get 5 over 5, gives us a unit length of 1. Add is x plus x, y plus y, z plus z. Subtract is a new vector with negative y, negative x, negative y, negative z. And the subtract is the adding a vector. There's a bunch of ways of doing this, but the one we got here is that we take each component and we subtract it from the other one. Now, there are two more things that we are going to need to know about. They're called the dot product and the cross product. Now, folks in here will be in one of three groups. There are those of you who have worked with 3D systems before, who are like, oh yeah, dot cross, easy, I know that. There are those of you who are like, I've never heard of this before. And there are those of you who did maths in high school. And are like, don't make me do this again. I'm not going to make you do it again. The two important things only things you need to understand. The JavaScript is going to do all the maths for us. What we need to understand is if you have two vectors, here and here, if the dot product of those two vectors is 0, they are parallel. And if they are intersecting exactly 90 degrees, their dot product will be 1. That's what matters for us, because we need to calculate which way things are bouncing off each other. And if two vectors collide in space like this, you imagine two spacecraft crash into each other, which way the ejector seat is going to go, that's the cross product. If they crash this way, it's going to go up there. If they crash that way, it's going to go there. It's the vector at 90 degrees to the two that you just banged together. That's it. That's everything we're going to do about dot and cross products. The JavaScript code looks like this. Now, all the code for this is online. It's on GitHub, and there's actually a full workshop walkthrough with all of these examples in it if anyone really wants to go and read up on this stuff afterwards. So we've got dot products, cross products, vectors, colors. Now we are going to, we have this. This is cool. This is a static factory helper method that makes things just a little bit more intuitive. Now, what we've got here is we've got a static property on vector called from that returns a JavaScript object with a to property, and the to property is a function that captures the initial vector, adds another one. What this lets us do is to write this code here. I want vector from here to there. And it will just go, oh yeah, you've given me 2 points, I'm going to give you a vector goes from here to there. So we got a second order function that captures the other one in a first order function. It's one of the nice things you can do in JavaScript, which is a little bit more difficult in some other languages. So we are going to project rays into space. What does a ray look like? This. We have a constructor. It takes the start. Where does the ray come from? And it has a direction. Which way is it pointing? And when we get the direction, we take the unit vector of the direction, because we don't care how long the ray of light is. We just want to know which direction it's pointing. And we have a method called trace. We give a ray of light a scene, and that ray is going to go bouncing off into that scene and tell us what color it came back with. And at the moment, all we've got is the scene background, because we have outer space with nothing in it. We need a camera. Camera looks like this. We are going to import the vector. We're going to import the ray. Camera takes a constructor. Now, camera in our world has 4 things. Location, where is it physically in space? Look at, what is it pointing at? Is it pointing up, down? What is the exact coordinate of the thing the camera is aiming towards? And then the width and the height, is this a wide angle lens? Is this a very narrow angle lens? And the same in the height, so we can get different shapes of frames and things, square frames, widescreen frames. We capture those in our constructor, then we do 4 lines of incredibly gnarly vector mathematics. We take a vector from the location to the look at. That tells us what direction the camera is pointing in. Not what it's pointing at, which direction it is pointing in. Then we are going to take the horizontal, basically imagine you're inside the camera, like you're sat inside the camera like this in your little camera suit. When we move the camera, it's going to point up, down, but for you, there is always going to be a direction which is on your right and a direction which is your up. So if we point the camera down, up is now over there and right is over there. If we swing the camera, up is over there, right is over there. We need to know those 2 vectors. So we calculate them using vector dot products and cross products and all that kind of stuff. That's what these are. This tells us which way the frame is oriented in space. Now, we have this chunk of code here. So we say, hey, I want you to trace this scene at these coordinates, x and y. Now, these coordinates are camera coordinates. They go from -half to +half. So we're going to say, right, take the right thing on the camera, scale that by the x. Take the up thing on the camera, scale that by the y. Invert it, because computer screens are upside down, because they have y is 0 at the top. I don't know why, they just do. Then calculate which ray points through that point on the viewfinder, create a new ray from the location of the camera in that direction, and say to that ray, hey, go trace yourself through this scene. Come back, tell me what color you found. Scene looks like this. We have a constructor. All we've got is a camera and a background. That's it. Nothing else exists in our universe at the moment. And we have a trace method that if we say to the scene, hey, trace yourself, it goes, all right, I'll ask the camera to do that for me. So the scene says the camera, trace through here. The camera goes, yep, says to the ray, go off, tell us what color you found. The ray comes back and goes, hey, I found the color of outer space. Look at me, aren't I special? We have a thing called the renderer. This is where we start mashing the kind of 3D coordinate system together with the world of the web, where this stuff is actually happening. Renderer looks like this. We have a canvas width and canvas height. This is on our screen where we're doing all the actual computery stuff. How wide, how high is the canvas that we are drawing on? We're going to capture those in a constructor. And then we have this, the render method. And this is the thing that says, all right, pixels by pixel. So each row, y, 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 take every pixel, x, 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 so px and py here are pixel x, pixel y, and transform those into camera coordinates. So we want to go from 0 across to 1280 pixels, and we want to map that into -half all the way through to +half. We do that in each dimension, and then we pass those into the scene. We say trace yourself at these camera coordinates, and then we pass the result to this callback function, which takes the x, the y pixel, and the color. Index.html, thing that actually runs in the browser, blah, 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 header. The 2 lines that actually matter, we have a canvas. Canvas is how you do 2D graphics in a browser. It's where you can draw stuff, pixel by pixel. And we have a JavaScript file here, script type equals module. This is the thing that says to the browser, we are running here in up-level modern JavaScript land. You can use ECMAScript, you can use modules, you can use exports. This does not have to work in IE6. Don't worry about it. You can relax. There we go. We have one more thing. We have main.js. This is the module that the browser actually loads. And what we do in here is we're going to say import all the things. Now, you'll notice here renderer re-exports everything that it imports. That kind of forms like almost like a hub for all of our dependencies here. Everything flows into that, and then it all flows back out the other side. Get us the canvas. Yeah, document.get element by ID. I'm sure most of you have seen that before. We want to get a 2D graphics context off that canvas. We say, hey, let's make a new renderer. Here's the canvas width, canvas height. Here is our callback function, paint pixel, x, y, color. It's like, all right, I will paint the pixel at x, y, and I will paint it, and we're using that color.html helper method there. We spin up a new camera. We create a scene. The background color is blue, and we say render, and we get, woohoo, look at that. This, trust me, this is not a camera trick. This is a real picture of blue outer space. And if we run it in a browser, we get that. 1.551 seconds to render that at 1280. Let's put some shapes in the world. So we're going to create 2 more files here, shape.js and sphere.js. Now, the way a sphere is defined in our world, it has a center. Where is it? Has a radius. How big is it? That's it. That defines what a sphere looks like. A sphere has an inside and an outside. Now, we need to be able to calculate, when we project a ray of light into the world, does it hit that sphere? There are 3 scenarios. It doesn't. It just goes flying straight past it and off into outer space. It goes in one side and out the other side. Or it just skims the surface, and we get a single intersect point. And what we need to do is to calculate the distances of those intersects, because we need to know which one is closest. Now, we're not going to go into the arithmetic of how we do this. This is the quadratic formula. If any of you knows that, b squared minus 4ac all over the root, if you remember the stuff from school. That's how we get the points where it goes in and out. And if it has no solutions, we missed. If it has 1 solution, we grazed the surface. And if it has 2 solutions, then it went in one side and out the other side. We need to measure those distances. The reason we need those distances, we need to know which shapes are nearer than which other shapes. If we have a scene like this, and we're going to project rays through this, this one here has 2 intersect points. This one has 6 intersect points, because it goes in and out, in and out, in and out of all 3 shapes. This one has 2. So first of all, we say to each shape, hey, which one of your intersect points is the closest? That gets rid of those. Then we say to the rays, well, hey, which one of those 3 nearest intersect points is the nearest point? That gives us these ones. That means we know what shape we hit, and so we can say to the shape, hey, what color are you? And that lets us know which color these rays of light come out. And that's how we do depth occlusion. It's how we can put objects in front of and behind other objects. So the code that is going to make this thing work, we'll talk about that in a second. We have an export class shape. Shape is an abstract base class. JavaScript does not have abstract classes. It has inheritance, but it doesn't have abstracts. So the constructor on a shape looks like this. We just tell it what color is that shape. It stores a reference to the color. We have a method called intersect. Now, the way to fake abstract classes in JavaScript is to have your base class throw an exception, throw an error. So if we accidentally create a shape and we forget to implement this intersect method for that shape, it's going to go, hey, classes that extend shape must implement intersect. It's going to fail straight away. We'll see that in the console. We'll know we made a mistake. We have a method here called closest distance along ray. We give it a ray. It's going to go, well, yeah, get me all of the intersects for that ray. Now, this filter method here, JavaScript has wobbly arithmetic because it has a single numeric type, and we are working here in tiny, tiny fractions. Have any of you ever seen the famous example in JavaScript, 0.2 plus 0.1 is not exactly equal to 0.3. It's almost equal to 0.3. Now, this is, I think, a reasonable design decision by the creators of JavaScript, because it means it has one numeric type that works pretty well for most things. It doesn't work pretty well for ray tracing. We are going to have a whole bunch of values in here which are almost 0, and we need to treat them as if they were 0. So threshold here is a tiny, tiny value, and we're going to say, well, anything below threshold, get rid of it. Effectively treat that as if it was 0, get rid of the 0 values there, and then find the shortest distance of the distances that are left and return it. That'll give us the shortest distance along that ray. Threshold is 0.0000001. If you see weird stuff, make it bigger. If that doesn't help, make it smaller. It is very, very difficult doing exact science here. Let's implement a sphere. Now, most of the behavior we need comes from the base class. All a shape needs to do is to implement the base class and handle its own intersect calculations. So a sphere has a constructor, the center, the radius, and the color. Passes the color up to the base class, and then constructs itself with the center and the radius. And then this is the Pythagoras in JavaScript, heavily optimized. This will return 2 points, 1 point, or 0 points. It'll return an array, a single value, or it will return nothing. It will return the empty array. There is a reason we are using the empty array. Does anyone in JavaScript know what the minimum value of the empty array is? It's infinity. Positive infinity. Because minimum is implemented by, hey, let's start with the biggest value we can find, and if we get anything less than that, then that's the new minimum. So if you don't give it anything, it gives you back the biggest number it can find, which is infinity. So we're going to take our array class here, and we're going to say, okay, well, instead of returning the scene background, we want you to calculate the distances to all the shapes on here. We want you to find the shortest distance. If the shortest distance is infinity, it means we didn't hit anything. Return outer space, the scene background color. Otherwise, find the shape which matched that distance and tell us what color that shape was. We are going to write a function called example scenes. This is like a library of standard scenes we're going to build up. So colored spheres here has a camera. Its at vector is 0, 1, 2 up, and -8 back. It's pointing at vector.z, so it's pointing just past the origin there. The background is black, and shapes here is going to be a new sphere, 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 sphere. Yellow, red, white, green, blue. We could go through and read this, but YOLO, let's run it and see what we get out the other side. So we run this thing, and, hang on, we need to do one more thing first. Yeah, in our main.js, this is the module our browser imports. We say, hey, example scenes, colored spheres, pass that to the renderer, run it, and we get this. And if we go in here, and we move the camera up a little bit, so instead of being at 2, we're going to move it up to 5, and we run it again. We're going to get this, and we go back in here. We're going to move the camera just a little higher, move it up to 15, so we're kind of looking down on the scene so we can see the configuration of those shapes. There we go. So these just look like flat disks of kind of brightly lit cardboard floating in space. But we can see we've got different shapes at different depths. Things know what's behind and what's in front. Let's have a look at lighting. Let's put lights in our universe, because lighting is what makes disks look like spheres. Now, lights in our world, they are points in space that light comes out of. They're not lamps. They're not lanterns. They don't have bulbs. You can't see them. You can only see the things which are illuminated by them. So a light has a position and a color, and it has a method here called illuminate. We give it a material, and we say, hey, tell us what color that material is at that point if it's this bright, and the light will go, oh yeah, I can do that. I'm going to multiply, I'm going to get the material's color, I'm going to multiply it by my color. So if I'm a red light, and that's a green ball, you're going to get 0, and then I'm going to scale it by the amount of brightness that was passed into this calculation here. Material is new. Material defines what things are made of. We need something a little bit more sophisticated than just colors. So we've got a get color at here, but then we are going to extend our color class so that it extends material, and get color at returns this. So instead of just being red, we now have red as a material because we can use material in this thing here, which is called appearance. And appearance controls the way things look in our universe, the way they react to light. We have a constructor with a default of gray. We have a get color at. It says, hey, well, the appearance contains a material, so ask the material what color it is. That's all we need to do for the moment. We need to know about something now called the surface normal. If you are standing anywhere on the surface of a sphere, the surface normal is the direction your head is pointing in. If you're standing on a big flat surface, the surface normal is the direction that your head is pointing in. We need to know which way is the surface pointing, or if you were to stick an arrow in it, which way would that arrow be pointing there? And we are going to extend our shape with get normal at. You give it a point and it tells you the surface normal at that point. Which way is the surface flowing at exactly that point? Shape doesn't know. Shape says, hey, you forgot to override this. That's your job. And we are going to extend our get color at method. Instead of just returning the shape, we're going to say, get the normal at this point. Which way is the surface pointing? Get black. We're going to start with black, and we're going to add colors up on it. Black is effectively starting at 0, right? Then we're going to say, hey, for each light in this scene, for every light in our universe, we want you to calculate the vector from this point on the shape to that light position. What is that vector there? What does that look like? Then we are going to take the dot product of the surface normal and the light. If the light is shining directly onto my face, I look very bright. If the light is shining across my face, it doesn't illuminate me nearly so much. If a light shines straight across a surface, it doesn't catch it. You get no illumination. If it's directly on, the dot product will be 1. We get full brightness. If it's directly across or parallel, dot product is 0. We get no brightness. If the brightness is less than or equal to 0, yeah, go, give up. Otherwise, illuminate. Say to the light, hey, light up this point by this much brightness. Tell us what color you get back. We add that to our running total. Return the color we got. Now, we need to do one more thing in our ray.trace method here. We're not going to return nearest shape.color. We're going to take that out. And instead, we're going to say, hey, find the point where the ray hit the object. Find the exact point on the surface where that ray of light hit us. And return the nearest shape, get color at that point in this scene. And the scene contains the lights. So the shape gets a thing saying, hey, if you were in this universe with all these lights, what color would you be at that exact point there? That then calls in, does the lighting calculation on that. So, our example scene, we need to upgrade our shapes so that instead of just being colored, our shapes have an appearance. And we need to add a set of lights into that scene there. These are the changes we make to this. We go into our browser, we press F5 to refresh it, we get this. It's looking good, huh? We're going to add 2 new shapes to the universe. Now, in 3D graphics, a plane is defined as you start in the center of the universe, you take the normal vector. This plane, which way does it point? It's funny to think of it like a plane having a direction, but this stage I'm on right now is pointing up because it has an inside and an outside, and the outside is pointing vertically towards the sky. That's the origin, that's the normal vector. We take the distance that the plane is away from the center of the universe, and that gives us a plane. A plane is not infinitely thin, and a plane does not have thickness. A plane divides the universe into an inside and an outside, and the normal vector on a plane is going to be exactly the same at every point along it because it's always the same. That's what it is. It's an infinite flat surface. We are going to define a box as a bottom left back corner and a front top right corner. Boxes in our universe are always aligned with the axes. We haven't got rotation in our universe yet. So that's a box. That's the inside of the box. And the surface normals on a box are what you'd think they are. The code for this is on GitHub. I'm not going to go through it. There's lots of it, and it's not very exciting. But we are going to go into our assorted shapes example here, and we're going to add a new plane. Vector.y means the plane normal points up, so it's flat. It's the ground, and it's white. We've got a box from -2 to 242, so it's kind of in the middle of the thing. It's like a 4x4 unit box. And we've got all those colored spheres that we already saw. We're going to go to our browser. We're going to press F5, control our refresh, and we get this. Now, this looks kind of weird because those shapes are sitting on that plane. They are resting on the floor, but we can't see that because the human visual system uses shadows for depth perception and proximity, and we don't have shadows. So we're going to add shadows. Shadows is kind of cool. We're going to go into shape, And we're going to say, right, I want every shape in our universe. If I give you a ray of light, tell me, do you block it? Like, are you going to cast a shadow for that right? So we've got cast shadow for, we give it a point, we give it a light vector, and it says, right, well, let me figure out how far away is the light. I'm going to create a ray that goes from me to that light, and I'm going to say, well, if this closest distance is less than the distance to the light, it means I'm in the way. I am between that point and the light source, so I'm going to cast a shadow, return true. And then down here, when we are calculating illumination, for each light, before we add any illumination, we say, hey, if any scene, if scene.shapes.sum, JavaScript thing returns true if any of the predicates in that return true, any element in there returns true. If anything casts a shadow, don't add light for this. If any of the shapes are shading that light, don't add anything to it. We run that through again, and we get this. In, what was that, 5 lines of code to add shadows to it? Let's make things shiny. Now, all the objects in this scene, they're made of the same material, but they have different surface properties. They have different, what's called finish. Some of them glow, some of them don't glow. Some of them are very, very shiny. Some of them are very, very dull. The top left one there, that's basically glow in the dark. Like, it doesn't matter if you shine a torch on it, it's going to look exactly the same. Bottom right corner, that's like a highly polished, like a snooker ball or something. We want to be able to simulate these properties on a surface. So we're going to create a thing called a finish, and we're going to inject 3 properties to it. Ambient is how bright is this thing when there's no light falling on it. This allows us to simulate things that glow in the dark. Also, it simulates daylight because, in most of the world, things are never really dark because we get a little bit of light scattering all over the place. Diffuse is how does this respond to having light shone directly on it. Like a high-vis cycling jacket, that's got a very, very high diffuse ratio. Something like a piece of black felt or these chairs in here, very, very low diffuse ratio. Light doesn't do a whole lot to them. And we've got shininess, 0 to 1. We have a default finish. That's it. 0.1, 0.70. Things are a little bit ambient, quite diffuse, and they're not shiny. We're going to go into our shape class here, and we are going to, first we need to pass in the ray as well, the ray of light that we are calculating on at the moment. We are going to get the ambient color on the shape at that point. This is our starting point. We don't start from black anymore. We start from the shape's ambient color. We calculate something called the reflex angle. Which way is that ray of light going to bounce when it hits us? And then we are going to say, hey, this appearance finish, I got a ray of light for you. Please add whatever highlighting you think is appropriate if that ray of light hits this point at that angle. That is in our finish class, so we add the highlight color. We go and take a look at what finish looks like, and we have this method here. If the shape isn't shiny, return black. Remember, returning black means add 0. Don't contribute anything to the total color. Otherwise, calculate the reflex dot product. How intense is the highlight at this point? Then, if that's less than 0, it doesn't matter. The light is in the wrong direction. It's not bouncing here. Otherwise, take 32 times shiny. Now, shiny here is between 0 and 1, remember? So we're going to get a value between 0 and 32. And then raise the intensity to the power of that. So if the shininess is 1, the intensity is going to be raised to the power of 32, which is how we get this very, very sharp defined edges, a very, very steep exponential curve there. And then scale the light color by that and give that back. That's our highlight method. We're going to jump over here. We're going to add shiny to all these things. Shiny, 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 shiny. Let's run it. Get that? Reflections? The first time I implemented reflections, I was like, it can't be that simple. This must be a trick. The way reflection works is you say, right, does a shape reflect between 0 and 1? How reflecty is it? Yep, that's okay. Now, what we're going to say in here is, all right, when we trace into a scene, first of all, we need to add a maximum depth. In real life, if you stand between parallel mirrors, you see into infinity. In JavaScript, if you do that, you see into a Stack Overflow exception. It's not nearly so exciting. So we say if a ray of light bounces more than 16 times, then stop iterating. So we're passing a depth parameter into a scene, into our trace method. If we've exceeded the maximum depth, return color.black so you don't add anything more. Otherwise, increment depth every time we recurse through this function. Then we're going to jump over here into our appearance class. I'm going to add a thing called reflect. Now I think this is brilliant. It says, well, if this doesn't have any reflection, return black. Otherwise, just start a new ray tracer. build a new ray from this point, pointing in the reflected direction, and trace it into that scene, just like we did at the very top level. We're recursing all the way down here. And then scale the result by the amount of reflection. So something with a reflection of 1, we get perfect 100% reflection. Reflection of 0, we get nothing. Anything in between, it'll contribute a little bit to the color on it. That's what our reflect method looks like. We're going to jump over into our shape class. And we are just going to, in this block here, going to drop in this thing here. Hey, this dot appearance dot reflect that point, that angle, this scene, this depth, and add that to whatever color we're working with. So we start with the ambient color, we add the reflection, and then we go through and figure out what each light in that scene is going to do. And we take all that, and we run that through our tracer, and we get this. Now, I'm lying. We don't actually get that. What we actually get is we get this. We press refresh in our browser, because all the renderings I've been showing you so far have been kind of simulated. The browser's going to sit and do nothing, and nothing, and nothing. And it's unresponsive while this is going on, because the browser only has a single thread, and the thread is currently busy doing maths homework. And eventually, after about 15 seconds, the browser is suddenly going to go, is that actually running? There we go, it's running now. Look at that. The progress bar's spinning. And we're looking at it going, well, this is very exciting. I thought 3D graphics would be more fun than this. And we wait, and we wait, and we wait, and we wait. And eventually, what we get coming back off this is finally it goes, oh yeah, there's your scene. I rendered it for you. Now, there's two things that we'd like to be able to do. One, we'd like to be able to see it as it's getting drawn, right? And two, it would be nice if the browser didn't become completely unresponsive for a minute or two while it is rendering our scene. So we are now going to introduce a thing. We got 3 minutes to do this. We're going to go through it at speed. We're going to introduce a thing called a web worker here. Now, workers and modules, you can't combine them in Firefox. It can't handle doing both at the same time. It'll do background workers, and it'll do ECMAScript modules, but Firefox can't do modules running as part of workers. All the other browsers can. So Chrome, Edge, Vivaldi, Safari, Brave, works fine in all of those, doesn't work in Firefox. We are going to create a new main.js method here. We have an update status. We say, are you running? And we toggle the status of 2 buttons based on that. Our render function now says, hey, spin up a new worker. Type equals module. We're using modules here in this thing. Add an event listener. Workers can't manipulate the DOM directly. All they can do is pass messages backwards and forwards. So we add a listener for that message. Post a message saying, hey, render at this width and this height. We add a listener there to the cancel button. Now, our worker class here looks like this. We have a callback function. Now, the callback doesn't draw a pixel. The callback sends a post message. Hey, draw this pixel at this point here. We're going to add an event listener to the message thing here, and that is going to unpack the message. It's going to say, hey, did you just ask me to render something? And we're going to say, yes, we did. And it's like, all right, well, in that case, I'll spin up the renderer. I'll plug your assorted shapes in, and I will render that scene using this callback. And when I'm finished, I will close myself and post a message saying I am finished. We have a message handler over here. Unpack the data. What did you get? If the worker said fill rect, then fill a rectangle. If the worker said finished, update status. Let's run it. Now, we're not seeing very much. There we go. Render's completed. This has been sped up for the studio audience here. The render's completed, and we've got this glacially slow. Like, hang on, it says render's completed. Like, that said it's done, right? What we've just done is we've dumped 1 million messages in a bus and told the browser to process them as fast as it can. The maths homework is finished, but every pixel has dropped a message into that queue, and we are churning through those messages as fast as we can. This is a really bad way of doing background workers. So instead, what we're going to do is we're going to make a callback here. It takes a thing called a uint8 clamped array. This is an array of unsigned 8-bit integers that doesn't care if you put in stuff that's too big or too small. It will just clamp it for you and bring it down to within those. It is brilliant for blocks of pixels. We are going to create an offset function here, an offset thing, and we are going to return a function, so a second-order function that returns a first-order function that says, hey, when you give me an X and a Y and a color, I'm going to put them in that buffer, and it's going to store things. And then when the buffer is full, I'm going to put the buffer into something called an image data, and I'm going to send that to the foreground thread. Post message, put image data. Put this block of pixels on the canvas at that point. And then over here, I have a handler that says, hey, put an image data at this point here. That's going to call context.putImageData, which is blisteringly fast, because this is what it was designed to do. So we're going to go in, we're going to run that. And we now get this real-time interactive. It's rendering it in blocks of about 20 pixels at a time. The browser remains responsive the whole time. And we can actually go in now. We have a render and a cancel. So if we start it running, we can get a little way through. We can go, oh, no, hang on, that's wrong. Cancel that, render it, start it again. We're going to go one step further with this. Our render function, we are going to call something called a partition function. It's going to carve the canvas into slices because we want multiple workers assigned to multiple processor cores, rendering multiple blocks that we are then going to glue back together when they get back out into our browser. So we're going to call this function partition the canvas into this many rows and this many columns. Code for this is in GitHub. I'm not going to show you the slide for it because it's really tedious maths. And we're going to say, hey, for each block, I want you to draw a stroke around it just so we can see the shapes of the blocks, and then run worker for that block. And this thing here is going to drop in, and our run worker for block looks like this. Create a new worker from that JavaScript function. Post a message to it. Hey, render this. That's the canvas width, that's the height. By the way, this is the block that we want you to work on here. We run this with 2 blocks side by side. We get 2 threads of parallelism. This is using 2 CPU cores plus another one to drive the foreground browser. Now, we can go a little bit further with this. We're going to go over by a couple of minutes, folks, but it is only a couple of minutes, and we are nearly there. This is the same thing running on 8 cores. Now, this is actually slowed down a little bit because the Camtasia screen recorder I used to make these slides interferes with the way the JavaScript canvas works. I don't know why, but this thing was twice as quick when you're not recording it. A little bit of Heisenberg's uncertainty principle there. This is the same thing running on 16 cores. Or rather 16. Now, I don't have 16 physical cores. So it starts as many as it can, and the browser waits until capacity is available, and then it spins up and it starts the rest. Let's go YOLO. Let's go a little bigger. Let's run 32 and see what happens. Now, at this point, it can only start about 8 of them. So the first 8 are going to start. Now, you can see where it's calculating reflections, it slows down. That's where it's got a lot of maths homework it has to cram into a very, very kind of short space of time. So you can visualize how these different threads and these different surfaces affect the rendering speed. And finally, just to see what happens, I put in 128 columns to see how this is going to work. And when you press go on this thing, at this point, it's significantly slower because the overhead of creating and managing all those worker threads loses you more time than you get from the parallelism. The sweet spot here is you want to partition your canvas into the number of physical CPU cores that you've got. Now, the very last piece that I want to show you today, just before we wrap up, is the canonical computer graphics hello world, which is shiny spheres sitting on a chessboard. So we need to make a chessboard. And we're going to make a chessboard by taking the universe, dividing it into black and white squares. Now, any point in the universe, we need to say, hey, is this a black square or a white square? So we calculate which row. In chess, these are called ranks and files. Calculate the rank and the file. If they are both odd or they're both even, the square is dark. If we have one odd one and one even one, the square is white. That's the algorithm that we're going to use. Now, think about a chessboard in 3D. What do you expect to see? Do you expect it to be squares all the way up? Or do you expect it to be like 3D squared patterns where it's checkerboard in both directions? There is code for both of these in the repo. You're welcome to go in and take a look at that. The one that I'm using here is called Chessboard. And the algorithm for doing this, we pass in the 2 colors, black, white, and the size of the squares. We say, hey, what color are you at that point? And we're going to say, we'll calculate which rank and which file of the chessboard we're on, and then do this. Bitwise exclusive OR them, and that with the number 1. If that's true, they're both odd or both even. If it's false, they're different. And return the color we get out of that point. We're going to go back to our example scene. We're going to drop in another shape here. We got a couple of boxes. We got a checkerboard box in the middle. And we are going to feed that thing into our rendering engine here. And that is going to come back, and that is going to give us this. And if any of you feel like abusing your phone, that is the source code that renders that image. I think, well, it certainly runs on iOS. I've tried it on iPhone and iPad. It runs pretty well as long as you've got Safari version 13 or above. It should run on Android, but when we tried it in the bar the other night, all the Android phones couldn't scan the QR code, which is why I added the URL below there. So there's a couple of parameters on there you can actually go in and play around with. You can move the camera. You can change the number of rows and blocks and stuff you've got on it. Folks, thank you very much for your time. We've overrun by a couple of minutes there. If you are interested in finding out more about this, go to that URL. There is a whole walkthrough of building this entire thing step by step, which takes a little longer than 45 minutes, as you can appreciate. But I hope you all enjoyed that. Thank you for listening. And we are over, but I will be out in the expo area if there are any questions.